In this exercise, you explore the difference in spline interpolation and how long range a small effect of a change of one coordinate point could carry over. So the task was that starting from two arrays with which you were provided, to find first a second array that takes the first value to be 10, but otherwise is exactly identical to the YS array that you had in the exercise. Now the task was to find two interpolants. So the first one, L, is a cubic spline where the boundary conditions are not a knot. Since this is a default, you don't strictly have to define it in this case. That's better to be safe than sorry. And then the task was to find a new interpolant, L prime, where the interpolation is done on the second array where the first entry is 10. So this is the function L prime. Now, it's always nice to just look at it and see what's going on. And this is now plotting those. So first I calculate some points that give a decent distribution over the domain we're interested in. And then I plot these two functions, because once you have a spline, you can call it just as if it were a function. And then you get, for every x point, you get the corresponding value of the spline. So in this case, we see the two curves, and we see that they differ substantially, even though the point change is actually at 0. So in this case, 2 units apart, and this carries over for quite a long domain. Now, the difference becomes smaller as you go to points farther away from that, which kind of makes sense. But the message here is that any change to a cubic spline is not strictly local. So then the task was to find a new function, q, which returns the absolute difference thereof. So here I make this a function, and what we see is that q returns the one spline inquired minus the other spline inquired, and then the absolute difference thereof. The task tells you that at 6 this value is close to 0.035, and indeed if we ask what's q at 6, we get precisely this, and if we ask what's q at 3.5, that's the answer to your task, so it's 0.11 and so on. For the second task, the formulation was a bit more mathematical, but the concept is similar. So we want to compare how cubic splines and B-splines act when serving as an integrand. So since they're smooth and they're polynomial, you can integrate them analytically, and this is one of the major advantages of using splines, or one of the reasons why people use polynomials as interpolant. So the task was first to take some data points where x and y are the same, going from 0 to 10, so 11 data points, and then to have two splines, so one cubic spline, LC, and a B spline, LB. So here you have the equivalent, so we have xi, we have yi with numpy a range, you can get this list. And then we have LC, which gives us the cubic spline, and then we have LB, which is the univariate spline, meaning the B-spline. Now, in order to make sure that the random numbers are always the same, so we change this random seed to 42, and then we say, all right, this is these 100 consecutive random vectors, epsilon I, that we need to choose. And we do that with the function numpy random normal, where you scale by some amount, then you give some size, where size is the number of data points that you get, and scale is the width of the standard distribution. So now we can get our yi prime, which are specified here, and these yi primes are just the yi that you already had plus this random noise. So it's nearly linear, but not exactly linear. So what we do is we generate a cubic spline over here, which builds on this yi prime, again with the not-a-knot boundary conditions, and then we use the univariate spline in order to get a B-spline entry on the same data points. Now they are not strictly the same, and we're going to investigate how much different they are by calculating these two splines over here, and based on those splines, calculate the integral. And sadly, they are called differently. So for the cubic splines, that's the function integrate that you need to look for, and for B-splines are called integral, but what they do is the same thing. Take the polynomial, integrate it, and then calculate the proper integral with the boundary conditions over the domain which you have specified. Now we wanted to have a quality metric, namely the difference between, so how much is the difference if you have and if you don't have the epsilon going into that. So luckily we have our initial fits over here, the initial splines. So what we can do is we can integrate this one from 0 to 10 and then yield the absolute difference. And the same for the B-splines. The logic is the same. Now again we have to use integral rather than integrate. Now the question was about the mean signed difference between the two, so QC minus QB, which is the difference that we append here. And now if you calculate the mean thereof, you see that typically QC is larger than QB, meaning that this epsilon, in our test case, influences cubic splines more than it does B-splines. So 0.02 might be small, but keep in mind that this means that when, depending on what integral method you choose, you're going to get a different answer for your interpolation.